Hello, ladies and gentlemen. Today, we're going to look at the beginnings of probability distributions. And we're going to start out by talking about random variables. And we're going to focus our energy right now on random variables of the discrete type. That is, a random variable that can be counted. Discrete random variables involve counts of things. And a random variable is it's an event that happens. And it takes on values as we perform the experiment that we're performing. And for instance, some discrete random variables would be the sum on two dice, like we see right here, or the number of cars in a parking lot. A probability distribution function, or sometimes called probability density function, assigns a probability value to each value of the random variable. And the notation that we use is the function is the probability that random variable x equals a specific value. For instance, if we roll a dice, so x is going to represent the face showing on a dice. On a die. We can represent this random variable using this table. So it's the values that x can take on are 1, 2, 3, 4, 5, or 6. And if it's a fair die, that is, if one face is not more likely than the other, the probability that x equals 1 is 1/6. The probability that x equals 2 is 1/6. 3 is 1/6. 4 is 1/6. 5 is 1/6. And 6 is also 1/6. This table is an example of how we would show a probability distribution function for a discrete random variable. Some properties of a probability distribution. This is true for discrete random variables, as well as we'll look at continuous random variables that share these properties. So the values for f of x, that is the values for the probability that x equals a particular value, have to be between 0 and 1. We saw that in our study of probability. The sum of all the f of x values, so the sum of all the probabilities for each x in A, where A is the set of all possible x's. Well, what do all of the probabilities have to add up to? They have to add up to 1. This probability distribution has to account for every possible outcome that could come from the experiment that we're measuring. So in the example that I had with the die, if you total up all those probabilities, they equal 1. They are representing every possible outcome. Those random variable values are representing every possible outcome for when I roll a die. So, an example. X is the random variable, being the number of heads obtained when you toss 4 coins simultaneously. Okay, what are the possible values of x? Well, we could get 0, 1, 2, 3, or 4 heads. Those are the values that x could take on. So our probability distribution, and this is a capital X equals lowercase x, we're going to have a 0, 1, 2, 3, 4, and that's it. Now we just have to find the probability of each of these things happening. And somehow we need to count up all these outcomes. And what might be helpful for us to organize this, instead of just listing everything out, would be to look at a tree diagram. We could get heads and tails. Heads or tails on the second flip. And so on like this. And what we'll find here is we'll find that there are 16 total outcomes. And one of those outcomes, we get 0 heads. That would be when we get tails on all of them. On four of these total paths, we'll find that we get exactly one head. So 4 out of 16, or also known as 1/4. What's the probability of getting exactly 2 heads? Well, we'll find that there are 6 paths through this tree where we get exactly 2 heads. What's the probability that x takes on 3? That is, that we get 3 heads? Well, 4 out of 16. And what's the probability of getting 4 heads? What's the probability that x equals 4? That's 1 over 16 again. So here's our probability distribution, and it's not a huge deal if you don't reduce, but you can see that all of these probabilities are between 0 and 1, and if we were to add up all of these, the total is 1. Those are the 2 criteria to be a probability distribution. Our next example, we have more of a mathematical probability distribution. Our probability distribution is given by a function f of y is equal to k times y squared, where y can take on the values 0, 1, 2, 3, or 4. Find k, and then draw a bar chart to represent f. Well, this seems fairly daunting at first glance, but if you remember that the sum of all the probabilities, and this is probability, the probability of each y value, the probability that y equals little y, those all have to add up to 1. So k times 0 squared plus k times 1 squared plus k times 2 squared plus k times 3 squared plus k times 4 squared has to be 1. And what we end up with is 30k equals 1. So k is 1/30. So my probability distribution, we have values for y. And the probability that event y takes on a specific value, the probability of 0 is 0. The probability of 1 would be 1/30. I'm just substituting 1/30 here and plugging in, substituting my different values for y. Probability that y is 2 is 4/30. Probability that y is 3 would be 9/30. And the probability that y is 4 is 16/30. So we could check and make sure that all of these do indeed add up to 1, and all of these are between 0 and 1. Good news. Now our graph. Now remember, a bar chart, it's kind of like a histogram, except the bars do not touch, and they're centered on the data value that they're representing. So I'm going to have a bar centered above each one of these values. What goes on my y-axis? Well, I need a scale to represent these probabilities. So it doesn't make sense to go by 1. I'm going to go by 3/30. So the bar above a 1 will go about 1/3 of the way up. Bar above 2 is going to go a little bit higher than 3/30. A bar above the 3 would go up to 9. The bar above the 4 goes up to 16, so a little bit higher than my last mark there. And there is my bar graph that is representing this probability distribution.